Hi, everyone. Welcome to the videos for Lecture 10 of Privacy in Machine Learning and Statistics. Today, we're going to talk about what are called advanced or strong composition results for differential privacy. So the setting is we've got an algorithm that has been built as the possibly adaptively selected composition of a number of smaller algorithms, each of which we know is differentially private. Okay, so we've got an input X, which is a data set, okay, and that is fed to some algorithm A1, and that produces output Y1. Okay, and then based on Y1, we choose another algorithm, A2, and we feed A2 the same input X to get an output Y2, and so on and so forth. So based on Y1 and Y2, we choose A3, and based on Y1, Y2, Y3, we choose A4, and so on and so forth. And eventually, we sort of choose, or we stop. We choose a final algorithm, A sub k. It produces output YK. So we've got say k minus 1 here. Okay, so all these algorithms take as input the same data set X and produce a sequence of outputs, and that sequence of outputs is used to choose the next algorithm that will run. Okay, so the next algorithm that will run is going to be a function of what's happened so far. And a nice example of that is Lloyd's algorithm that we saw in lecture 5 or so. And also another example will be gradient descent, which we'll see in next lecture, lecture 11. Okay, so these are examples where the computation to be done at a given stage of the algorithm, the exact computation to be done depends on what came before. But the way we set up Lloyd's algorithm, the differentially private version of Lloyd's algorithm, we were sure that each iteration of the algorithm was still differentially private. Right? So the question is, like, if we know that A1, A2, up to AK are each, if each one of those is epsilon delta differentially private, no matter what particular sequence of outputs we saw. So like Y1 through Yj minus 1 are used to select A sub j. Okay, and what we want is that no matter what that previous sequence of outputs was, the jth algorithm is always going to be differentially private. And let's just say they all have the same privacy parameter, although these composition theorems work just fine when there are different privacy parameters for each algorithm. They're just like a little more complicated to state. Okay, so this is our assumption that each of the pieces is differential, epsilon delta differentially private. Okay, and then the question is, like, what can we conclude about A? The whole algorithm A. So we're going to call this whole thing A, big A. And so what can we conclude about A? Well, so, what we saw last lecture and in lecture 5 was what are called basic composition statements. And that says that, A is like epsilon, well, here, let's write it this way. So A is epsilon tilde delta tilde dp. Basic composition says that epsilon tilde is, k epsilon, or at most k epsilon, right? And delta tilde is at most k times delta. And so that we get this kind of linear scaling in epsilon, which is nice. It gives us this kind of graceful degradation of the privacy parameter. But in fact, with epsilon delta differential privacy, we actually can get a much stronger type of statement. Okay, so what's called advanced or strong composition, which we'll see. That's the subject for today. So what that says is, it says the following theorem, that epsilon is, well, I'll write out the full formula and then we'll sort of talk about the asymptotics. Okay, so epsilon can be taken to be epsilon tilde can be taken to be the original epsilon times square root of 2k, so something more like square root of k, times log of 1 over a new parameter, delta prime, plus some another term, which I'll get to in a second. And here delta tilde is k times the original delta plus delta prime. So we get to choose delta prime to, get the exact delta tilde we want. And then depending on what delta prime we put in, we get a log term, log of 1 over delta prime in the expression for epsilon tilde. And then we get a second term here in epsilon tilde, which is k times epsilon times e to the epsilon minus 1 over e to the epsilon plus 1. And the way you should interpret this whole expression here is that this is something like k epsilon squared when epsilon is, say, less than 1. And so notice that is, k, that's sort of epsilon square root of k all squared. So this term is smaller than the previous term as long as epsilon squared of k is less than 1. So if in particular, if epsilon is less than 1 over square root of k, then this second term basically doesn't really matter, at least asymptotically, and it doesn't make a very big difference in practice either. What really tends to what dominates is this this first term here, this one. All right, so this is our theorem that the adaptive composition satisfies this property that it's epsilon tilde, delta tilde differentially private, where epsilon is about epsilon tilde is about epsilon times square root of k ish. Okay. So, in terms of crude asymptotics, think epsilon tilde is about epsilon square root of k, and delta tilde is about delta times k. Okay, so the delta, but we think of the original delta as being selected normally to be quite small, and so that wouldn't affect the composition very much. And so all that really, that term, k, multiplying that by k shouldn't be too bad. What's really going to be, what you have to manage is the blow up in epsilon. So the rest of the lecture is going to be devoted to sort of understanding this theorem and then understanding why it's true and seeing a proof of this theorem, or at least most of a proof of this theorem. So let's think through what this tells us. So, for example, okay, let's take some examples. So first of all, let's just do a numerical example. Say each of the individual algorithms is epsilon, which is 1 in 1,000, 1 over 1,000 differentially private, and delta is 0. So it's each of them individually is epsilon 0 differentially private for epsilon equals 1 over 1,000. And let's say we take k equals 500. So then with these settings of parameters, if we go with basic composition, we'll get something like epsilon tilde equals to 0.5. But with advanced composition, we get something quite a bit smaller. Let's say if we set delta tilde to be about 10 to the minus 6, then we get epsilon tilde something like 0.1. Okay. So we get like a much smaller value for the actual privacy leakage. And in fact, you can sort of make this by taking very large values of k, you can get like arbitrarily big separations between what you get from basic composition when you get what you get from this more subtle advanced composition. Another example, to take a task we've talked about a lot, suppose I have suppose we have k adaptively selected count queries. Okay, so we've what we saw with the Gaussian noise last lecture is that if we select, if those k count queries are selected ahead of time, then with Gaussian noise we can add something that scales roughly like square root of k, whereas with Laplace noise, the Laplace mechanism, the analysis we've seen anyway, would scale with something more like k. Okay, so let's just think through what we know how to prove if they're selected adaptively. So if these count queries are chosen online, like, based on the answers to previous count queries. So like imagine an analyst who's working with like a Python notebook asking queries one at a time. Okay. So, so if we use the Laplace mechanism plus to answer each query and then use basic composition, then what we'll get is if we sort of work out what happens, we get noise about k over epsilon tilde per query. Okay, and there are extra log factors if you want the worst noise added to any query, but we'll stick with the per query noise for now because it's simpler. So, I guess I'm not working out the exact calculation, but basically you set the epsilon for each individual execution of the Laplace mechanism to be epsilon, your final thing, epsilon tilde divided by k, and then you get this much noise per query. If you were to use the Gaussian mechanism to do this, and again use basic composition, then we'd have noise something like, again, k over epsilon tilde times square root of log of k over delta tilde. And again, that's because you'd set the parameter of the Gaussian mechanism to add noise to be about, if you're using basic composition, you'd set the parameter, the epsilon parameter of the basic Gaussian mechanism to be something like epsilon tilde over k, and then this is the kind of behavior you'd get. On the other hand, if we use strong composition, even if we just use the Laplace mechanism to answer each query, then we're going to get something like noise that's much smaller, something like square root of k over epsilon, over the final guarantee, epsilon tilde, times about square root of log of 1 over the final delta. Okay, and so that's much better than what we get from either the Laplace or Gaussian mechanism with basic composition, and it's actually comparable to what we get with the analysis of the multivariate Gaussian mechanism with like a fixed set of queries, where the queries aren't selected adaptively but are all specified ahead of time. And actually, if we use, just to see what happens, if we use the Gaussian mechanism plus this version of advanced composition that's at the top of the page, then actually you get something similar but slightly worse. You get square root of k over epsilon tilde times log of 1 over delta tilde. So that's like, this we're happy about. This, maybe not so great. It's because it's actually a little worse than what we get using the Laplace mechanism. Now, it turns out there's a different and tighter analysis of the adaptively used Gaussian mechanism that would recover the same expression as we had above. But that you need to dig into a little more of the mechanics of the Gaussian mechanism to see how that works, which we're not going to do. Okay, so these are, this gives you a sense of why this adaptively selected, this strong advanced composition theorem is really useful. And it's going to really shine when we consider these algorithms that have many phases, each of which we can prove is differentially private. And we'll see an example of that when we talk about gradient descent. In typical applications on deep neural nets, this is being run dozens, possibly hundreds of times, so that the k parameter is really big, and so that square root of k factor can really matter a lot. Okay, so let's move on. So that's some examples. So let's try and understand, if we can, why it is that this thing is true. Okay. Maybe just one last point I'll make. We can get tighter bounds for specific mechanisms. So the theorem in the red box above is not sort of tight for all mechanisms. It's the best thing you could prove in full generality. And today we're going to focus on trying to get an analysis that's A, as simple as possible, and B, as general as possible. And then we're not going to worry too much about trying to fine tune it for different algorithms, although there are lots of results like that out in the literature that show how to do that. Okay. So the question is, why is this theorem true? And to understand that, it helps to take a sort of slightly, a particular perspective on the way we've analyzed differential privacy for different mechanisms. Okay. And I'll call this perspective sort of privacy loss as a random variable. Okay. And all right, so given an algorithm, a randomized algorithm A, and two different inputs, x and x prime, and a possible output y, we'll define the following thing, which we're going to call the privacy loss at y. So this is the log of the odds ratio of the probability of the likelihood we would see output y given input x versus the likelihood of seeing output y given input x prime. Okay. And for continuous distributions, it's okay to replace these probabilities with probability densities, okay, if the distributions have a density. All right, so this is a deterministic function. Notice that there's no random variable here. Once I tell you x prime, and y, there's just one number. But in some senses, this tells us kind of how much information have we gained about whether or not, based on the output, about whether or not the input came from x or came from x prime. So we can think of this quantity itself as a random variable if we're considering not a specific output, but a random output. So suppose we select a random output from running the input on dataset X. Okay, and so we can look at the random variable, which is this sort of privacy loss evaluated at this random output, on this random output drawn under input X. Notice things aren't quite symmetric here. X is in the numerator, X prime is in the denominator. And I'm choosing to look at the distribution of y on input X, the one that's in the numerator. Turns out that's the right way to do it. Okay, so last lecture, what we saw is that, like, if for all neighboring data sets X and X prime, if we always have that the probability over y, drawn according to A of X, that if we have that this privacy loss is bounded by epsilon with high probability, then the mechanism, this algorithm A, is epsilon delta differentially private. So this is the basic tool. This was sort of, I think, called lemma 1.4 in that lecture. So this tool is very useful for proving that things are epsilon delta differentially private. And that's the one we're going to use today. And now what this lemma tells us is if we can get a high probability bound on the value of this information loss random variable, then we'll be able to get, the result we want. And like in the theorem, these are going to be, in the theorem we actually proved, these are going to be tilde values because epsilon and delta are going to be the parameters of the original outcome. Okay, so incidentally, this condition is like not quite equivalent to differential privacy. It's not the same as saying that A is differentially private, but it implies that. And morally, it's the same. And we'll see a kind of a more precise reason why it's morally the same later this lecture. Okay, so we want to understand this random variable. So when the algorithm A is the composition of several algorithms, so A1, A2, up to AK, then the probability of seeing a given sequence of outputs, Y1 through YK, right? That's the probability that A1 produces Y1 times the probability that A2 produces Y2, given that Y1 was the output from X1. So we'll take X2, remember, takes Y1 as an input. That specifies the exact behavior of X2, and then it's run on data set X. So of A2, sorry. It specifies the exact behavior of A2, and that's run on data set X. So we'd get times that. Okay, so, and then, we can keep on doing that decomposition all the way down to AK of X, where AK of X is chosen based on Y1 to YK minus 1. Okay, so let's maybe write it this way, it's easier to read. So the probability we're interested in understanding is a product of probabilities. And that means that if I look at the information loss random variable, or the information loss for A on a particular sequence, Y1 through YK, so that's a log of, it's the log of a ratio. And each of the numerator and denominator are products. And so we can write that log as a sum. Okay. And so what we get is the sum from J equals 1 to K of the log of like the ratio of the appropriate conditional terms in the product above. So we get on top, we get the probability that J of X, once we've fixed Y1 to Yj minus 1, produces Yj over the probability that Aj of X prime, given the same output stream of outputs Y1 through Yj minus 1, would produce the same output Yj. Okay, so I can think of this as this itself is basically just a sum of little privacy loss random variables for each of the algorithms in the adaptive composition. So I can view this as like the privacy loss at Yj for an algorithm. So I guess we didn't really specify the algorithm here, but if we wanted to, we would put it up there. So this is for the algorithm Aj, where we've fixed Y1 through Yj. Okay. So even though the Aj is being selected adaptively, because in the numerator and denominator we're using the same sequence of outputs, we're still looking at the behavior of like the same algorithm AJ in the numerator and in the denominator. Okay? Because the y values that were used to select AJ are the same above and below. So what's kind of great about this technique, this way of viewing things, is that we don't need to know anything about the way AJ is selected from the Ys. Like that could be done by some automatic process, but it could also be done by a human analyst who's like, looking at outputs and thinking about what they want to know next. Okay, so there's no need to understand how A sub j is chosen based on y1 through yj minus 1. All we need to know is that that whatever AJ is chosen is going to be epsilon delta differentially private. All right, and so that's a very useful thing, because for example, in Lloyd's algorithm, again, we're choosing the exact computation to do it at stage t or whatever stage j based on the kind of cluster centers from the previous rounds. And so we need that, we really need to take into account the fact that adaptivity is present in the sequence. But the nice thing about this perspective is it allows us to kind of decouple that part of things and not worry about it. Okay, so what have we got? We've written the information loss random variable for the entire algorithm, okay, as a sum of little information loss random variables. And so basically, all we need to do to understand the behavior, to get what we want is a high probability statement about the sum. We want to show that the sum is at most epsilon tilde with high probability. But now we're writing this as a sum of random variables. And so it's sort of enough to kind of get our hands on what each of these individual random variables looks like. So to prove basic composition, let's say for epsilon 0, dp algorithms, all we need to do for epsilon 0 dp algorithms, what we know is that each of the terms in the sum is each term is at most epsilon. And so that means the sum is at most k times epsilon. Okay. So the proof we did in lecture 5, boils down to just looking at the sum. We proved it for two things at a time. The proof we did in lecture 5 just boils down to looking at this sum and saying something about it. To prove advanced composition, we're going to have to work a little harder. And we really have to look at sort of the whole sum all at once. Okay. So the idea of advanced composition is to show roughly that each term has expectation something like epsilon squared. Okay, and it's not actually true that these terms, in fact, these things don't even need to have finite expectation. That's one of the things that makes this tricky, but they have expectation roughly epsilon squared after we remove some set of bad outcomes. We remove a bad event from the probability space, and we'll see how to do that. Okay. So what I'd like to do before proving this, making that statement precise and proving it, I want to go through a couple of examples to work through the privacy loss random variables we get for some specific mechanisms that we've seen, so that you see like how this plays out in, in these examples. So let's see some examples. So the first example is the Gaussian mechanism, which we analyzed last lecture. So suppose we add so say we have a function. Okay, say f has L2 sensitivity delta, and a of x is f of x plus z, where z is normal with mean 0 and variance sigma squared, and sigma is, well, we showed we could choose it to be 2 log delta times 2 big delta times log of 1 over little delta over epsilon. Then actually the proof from last lecture showed the following. It wasn't stated exactly this way, but it's pretty much like, pretty much exactly this, is that the information loss random variable at output y, so at output, actually f of x plus z. So this is when we run, what we get when we run the algorithm on input x, is delta squared plus or minus, I guess, to delta z over 2 sigma squared. Okay, so because z is normally distributed, this thing, the distribution of this thing is normal with probability mean delta squared over 2 sigma squared, and variance delta, if you work it out, delta over sigma all squared. All right, so now the because of the way we set sigma, this is the same thing as having mean epsilon squared over 4 log 1 over delta. The constants don't really matter, but the point is that it's about epsilon squared, and variance about epsilon over square root of log 1 over delta. Or sorry, standard deviation about epsilon. Okay, so when you look at this, what you should be thinking here is this is something like epsilon squared, and this is something like, the standard deviation is something like epsilon. Okay, so even though like the statement we use about the Gaussian mechanism is that the probability that this random variable, this information loss, exceeds epsilon is at most delta, we actually know a lot more about it. We know that its mean is at most epsilon squared, and its standard deviation is at most epsilon. In fact, less than that, because there's log 1 over delta terms, but let's ignore those for a second. All right, let's look at another example. Let's look at randomized response. So in randomized response, what do we get? We get that recall that the way the mechanism works is given input x, we output a sequence y1 through yn, where yi is equal to either xi with probability a little bigger than a half, e to the epsilon over e to the epsilon plus 1, or the opposite of xi with probability, with the remaining probability 1 over e to the epsilon plus 1. Okay, and the important observation here is that their ratio is exactly e to the epsilon. Okay, and so what that means, if I look at the information loss random variable for this a given output, if x and x prime differ in position I, then the information loss will be 0 for all the other positions, like all the other, the only component that can tell me information about xi versus xi prime is the component relevant to person I. And so the information loss for any variable will be equal to plus epsilon if yi is equal to xi, and minus epsilon if yi is equal to xi prime, where here I is the place where the position where x and x prime differ. X and x prime differ. Okay, so this is what our privacy loss looks like. It's always either plus epsilon or minus epsilon. That's why that's why this mechanism is differentially private. But we can also say a lot more, but we can write down exactly what its expectation is. So the expectation of this value, when I plug things in, plug in the random output on input x. So it's going to be epsilon with probability e to the epsilon over e to the epsilon plus 1, because that's the probability with which I output xi. And it's going to be minus epsilon with probability 1 over e to the epsilon plus 1. And so when I put these things together, I get epsilon times e to the epsilon plus 1, minus 1, sorry, over e to the epsilon plus 1, which is basically epsilon squared over 2 when epsilon is small. Okay, so for epsilon, less than 1 roughly. I mean, this is for epsilon, like, smaller than, let's say, 0.1 or something like that. As epsilon gets close to 1, the constant out front will change, but it won't matter too much. Okay, so again, we looked at this, on one hand, we know this privacy loss is between epsilon and minus epsilon, but the expected privacy loss is only epsilon squared. It's a much smaller quantity. Right? Remember, we're going to apply these tools in settings where the original epsilon you start with is really small, like 1 in 1,000 or something. And so what that tells us is, again, if we're to run many copies of randomized response, the sum of the privacy losses will accumulate very slowly, because it's the expectation of that random variable. It's a sum of independent terms where the expectation is very small. Okay, so let's do one more example, which is the name and shame algorithm, another one we've seen a few times. So recall name and shame. The idea is on input X, I produce, again, a sequence of outputs, 1 per person, where yi is either person i's data in the clear with probability delta, or its bottom, just some, I'm not going to tell you anything, with probably 1 minus delta. And so if I look at the information loss random variable for name and shame, what's it going to look like? It's actually going to be, it'll be, take on 2 values. So if person i's data, so again, I is the value at which the neighboring data sets, the only value we care about is the place where the neighboring data sets differ. So if xi is revealed, then we get, when xi is revealed, we get an output which can arise on input x, and it rises with probability 0 on input x prime. So in fact, in this case, the privacy loss is infinite, right? We're basically broadcasting person i's data. There's no uncertainty left at all for someone on the outside or an adversary on the outside. Infinite privacy loss. But then if xi is not revealed, if bottom, if like yi is equal to bottom, then there's no privacy loss at all. Okay. Again, here, this is where I is the position in which x and x prime differ. Okay, so this is like a funny example. It's a different example. So notice in this case, the expectation is infinite. So that kind of sucks, maybe. On the other hand, the expectation is only large because of this like small probability terrible thing, right? There's this like catastrophic failure with probability delta, and otherwise things are good. So so what I want to say, what's the silver lining? But like, if we kind of ignore this event that occurs with probability delta, then actually we get a very small expectation. In fact, the expectation is 0. Okay, so that makes us happy. And what that suggests is, again, that, as long as, if I'm just going back a second to looking at the sum that we care about, it's at the top here, as long as we can argue that, as long as we can sort of take away these these k bad events, one for each of the algorithms we run, if we can somehow separate those k bad events out, then among what's left, we'll have a sum of random variables with very small expectation, and we'll be able to get like a tight band. Okay. And so this is the intuitive reason why strong composition holds, is that even though each of these terms individually varies between, roughly between minus epsilon and epsilon with high probability, most of the time, the sum, you'll get a lot of cancellation in the sum. And the sum of these random variables will be much smaller than k times epsilon. In fact, more like epsilon times square root of k. So coming up in part 2, we'll see why this phenomenon happens in general. Why this happens for every DP algorithm. Okay, so that's after the break. Stay tuned.